Okay, so welcome everyone to lecture 5, and time flies fast because I suppose uh, by the next lecture almost half the course will be over. Okay, so let's begin. So we will, as always, recall a bit of what we did in the previous lecture, and yeah, I hope everyone can hear my voice and see my presentation. So in the previous lecture, sorry, yeah. In the previous lecture, we defined what are ordinary points and what are singular points. And further, singular points were classified into regular singular points and irregular singular points. So irregular singular points were the bad points, but regular singular points were the good points, and where we could still solve the differential equation using power series method in a small neighborhood of the regular singular points. So let's just recall that, how we did that. Okay. So consider the ODE. So when we have a regular singular point, and we are just going to, for simplicity, we are always going to assume that the point we are talking about is 0 instead of x naught. So consider the ODE x square y double prime plus x bx y prime plus cx y equal to 0. So where b of x and c of x are analytic around 0. So we assume that b of x is given by this power series, summation I greater than or equal to 0 bi xi. And c of x is also given by this power series, summation I greater than or equal to 0 ci x to the power I. So everything is happening around 0. And motivated by what we did in the ordinary case, uh, what we did was we tried to solve the above equation by trying a solution of the type y of x is equal to summation n greater than or equal to 0 a n x to the power n plus r. So r is a fixed real number. So we can write this as x to the power r. We tried solutions of this type. We were trying to investigate if we can find a solution of this type to this differential equation. So that was a question. That was our guess. So okay, yeah. Anyway, I don't want to motivate that anymore because we already saw enough of that last time. So, and what did we do? As always, we substituted this into the differential equation. We substitute this power series into this differential equation. Yeah. And we got an expression of this type. And we will get some expression of this type. Right. And I have explained what are the ENs. So summation n, so this power series summation n greater than or equal to 0, En x to the n plus r. And we want to equate all the coefficients to 0. So when we do that, so the point is E0 is equal to IR times A0. So if we want E0 to be 0, then we want I of R A0 to be 0. So here I of R is the initial equation, which is very important. And I suggest you remember this initial equation. In the quiz, which is going to happen on Tuesday, there's going to be one question related to this. So you don't want to be deriving this complicated expression and the initial equation in a 1-hour quiz. So you just remember this. It's not difficult to remember. So I of R is R into R minus 1 plus B0 times R plus C0. Here B0 is the B0 coming from the power series B, and C0 is the C0 coming from the power series C. Okay, so E of 0, so the coefficient when n is equal to 0 is I of R A0. So we want this to be 0, that's one thing. And so what we do is we set well, okay, let me come. Yeah. And for all n greater than equal to 1, the expression En is the LHS of this equation. So when we want En to be 0, that's same as saying that we want this expression to be 0. And if you note, and the important thing we noted was that in this expression, we have I n plus r times an, and all these remaining terms, they involve the smaller ais. I mean, they involve a0 up to an minus 1. So this kind of gives us a chance. I mean, there's some hope that we might be able to solve for the ans in terms of the smaller ais, which is what, yeah. So that is a theme which came earlier in this course also. So this is something which we are familiar with. Okay. So the question is, can we find coefficients ans which satisfy the above two conditions? So we fix a0 to be 1, and for condition a to hold, we need that I of r should be 0. So remember, so here we are fixing a0 to be 1, and if we want this first coefficient to be 0, we want I of r to be 0, which means that r should be a root of this quadratic equation. This is the initial equation, and we assume that yeah, we will only analyze the case when the roots are real. So we assume that the roots are real, and we denote the roots by r1 and r2, and we assume that r1 is greater than equal to r2. So then we can inductively define for n greater than equal to 1 the ans in terms of a0 up to an minus 1 as, now when we define this ans, when we are going to define ans using this equation over here. So what will we do? We will take this term over here, we will take it to the right hand side, and we will divide it by I of n plus r. So we are going to plug in r equal to r1 into this equation, and what we need is that if I n plus r is 0, then we will be in trouble. I mean, we cannot solve for ans. So what we will need is that I n plus r1 should never be 0, but that is true because r1 is the larger root of this equation I of r. So remember, I had explained this last time. So we have this, we have the real line. Okay, let me make a line. We have the real line, and let's say r2 is somewhere here and r1 is somewhere here, and I of 1 plus r1 is here, I of 2 plus r1 is here, I of 3 plus r1 is here, and this is a quadratic equation, so its graph looks like this, something like passes through this, right? And so it's never going to vanish at these points, right? So that, yeah, so therefore all the ans will be defined. So we can find one solution like this. And similarly, the second point was if we plug in, if r1 minus r2, this is also something which we saw last time. If r1 minus r2 is not an integer, then when we look at the points, I of 1 plus r2, I of 2 plus r2, I of 3 plus r2, I of 4 plus r2, and so on, this these points will never be equal to r1 because r1 minus r2 is not an integer, and therefore I of n plus r2 is also never 0. So that is what I've written over here. Similarly, if r1 minus r2 does not belong to integers, then we can define another solution by taking, we just plug in r equal to r2 into this equation, and then we inductively solve for the ans, right? And we can do that since I of n plus r2 is never 0 for n greater than equal to 1. So for this, we need r1 minus r2 should not be an integer. So this was like a really nice, interesting idea, and it worked. And it's quite amazing that it worked in many cases. So today we will analyze the remaining cases. So that is when r1 is equal to r2 and r1 minus r2 is a positive integer. So when it is 0, so r1 minus r2 is always going to be greater than equal to 0 because we have taken r1 is greater than equal to r2. So we will do the two cases separately. The case when r1 is equal to r2 That is when r1 minus r2 is 0, and the other case is when it is a positive integer. Okay. So this was the content of the previous class. So I hope there are no doubts. So let's go ahead. Okay. So the idea is very nice, and it's also, yeah, mm, yeah. We are going to, yeah. Okay, so let's see. So first we are going to consider, so we are first going to analyze the situation where R1 is equal to R2. Well, it's in, I mean, the basic idea is the same in both cases. So we consider this differential operator L, which is given by x squared. So what do I mean by this differential operator? So L is simply a map. So we can take, we can take the set of twice differentiable functions. So we, let's say, okay, let me for simplicity, let me just take 3 times differentiable functions. Yeah. Let's just say, let's just take analytic functions. Analytic functions. Functions analytic in a neighborhood of 0. To the same set. Analytic functions. Right? So we take a function f, and this maps to, yeah, and when, I mean, the word operator usually means it's a map from one set to another. Okay. So it takes f to lf. And what is lf? Lf is by definition x square. So let me just use some shorthand notation, which is familiar to everyone. X square f double dash x plus x bx f dash x plus c of x into f of c of x into f of x. Okay. So our aim is to find solutions to this equation L of f is equal to 0. Find f. Okay. So for this, uh, what we do is we consider a function of 2 variables. Okay. This is psi of r and x, and this is defined as n greater than or equal to 0, a and r times x to the power n plus r. Okay. So right now we don't know what these functions a and r's are. We have to try and solve, we have to find these functions a and r's. But of course it will be related to something which we have seen previously. Okay. So this is, so let me just emphasize, yeah. Function of r. A and r's. Okay. Okay, great. So one easily checks that L psi Rx is equal to summation n greater than or equal to 0 En x to the power n plus r. So where the Ens are given by this as follows. So this is an easy check which you can do. Okay. Once again, I is the initial equation. Okay. Okay, great. And now okay, I have already written this. Okay. IR is the initial equation given by r into r minus 1 plus b0 r plus c0. The roots are r1 greater than or equal to r2. Okay, this sentence is not so much important right now. But let's just go back and let's just stare at this so that, yeah. Let's just pause over here for a second. So, yeah, and let me just repeat what we did. We took this function of 2 variables and we computed this. We applied L to this. Now this, so this is a function R. So d by dx is going to do nothing to the R. It's going to do to the other stuff. And when we, yeah, so d by dx is only going to apply on the x to the n plus r. So when we apply this operator, you can check that the result is going to be summation n greater than or equal to 0 en x to the power n plus r. And for simplicity, I have used En over here because otherwise I don't want to write this complicated thing. So E0 is like this, and for n greater than equal to 1, En is like has this expression. Okay, great. So let's go ahead. IR is an initial equation. The roots, it's not so much important right now. So we set A0R equal to 1. So this is a function now. We take this to be the constant function. Okay. We said we take A0R to be the constant function. And then the equation En equal to 0 allows us to define the functions A and R. So let me emphasize now that these are functions, okay? So we are now defining functions A and R. All right. So, but there's no reason that this function has to be this. So yeah, this could be a bad function. For instance, A and R, I mean, it is, uh, sorry. Anyway, it's going to come later on. So let me not write. But I just want to emphasize that these are now functions. And let's just go back to this equation. So A and R as a function is defined in terms of the A0R up to AN minus 1R inductively. So this expression over here is a function, and we just A and R is this function divided by this function I of n plus r. Okay. Note that each A and R is a rational function in R. In fact, the denominator of A and R is product I equal to 1 to n I of I plus r. Okay. So a rational function means just a ratio of polynomials. A rational function means ratio of polynomials. Yeah. So this is obvious because if you just look at this equation, yeah, right. So you will get, yeah. So yeah, if you just stare at this equation, then it is going to be immediate that A and R is equal to some polynomial in R divided by the product as I have written there, I equal to uh, 1 to n I of n plus r. I of I plus r, sorry, not n plus r. Okay. So let's go ahead. Uh, the functions A and R are analytic at R1. So because, yeah, so why are these analytic at R1? Okay. So why are these analytic at R1? So remember, what did we see? A and R is a ratio of polynomials. There is some polynomial P of R over here divided by uh, I of 1 plus R, I of 2 plus R, dot, 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 up to I of n plus R. Right? Now, the numerator is, of course, analytic. And I mean, it's analytic everywhere. And when we took a ratio of two functions, the denominator as a polynomial, it is analytic. And when we took a ratio of functions, if the denominator did not vanish, then the ratio is also analytic, right? So at R1, the denominator does not vanish, does not vanish at R1, right? And therefore, this A and R is analytic at R1. Similarly, if R1 minus R2 is not an integer, then the function A and R is also analytic at R2. So that's what I've written. So A and R, these functions are analytic at R1, and if R1 minus R2 is not an integer, then they are analytic also at R2, simply because the denominator, the A and R's are a ratio of polynomials, and the denominator does not vanish. Okay. In particular, if we put R equal to R1, then it gives a solution since this thing happens. So I should have, yeah, maybe put something over here. So with these functions A and R, once we substitute these functions A and R's, so by definition, so let me, with the functions A and R, we have L of psi Rx applied on, I'm sorry, let me just make a writer on new page. Yeah, because that's something which is going to be useful. Oops. Okay. So with the functions a and r defined using en equal to 0. So all this is happening for n greater than equal to 1. A0r we define to be 1, right? So this implies L of psi of Rx. This was equal to summation n greater than equal to 0 en x to the power n plus r, right? But our a and r's are defined using the equation en is equal to 0. So we will only be left with, so en equal to 0 for n greater than equal to 1. So we will just be left with E0 x to the power r, and E0 is exactly I of r, A0r x to the power r, right? And A0 we took it to be 1. I'm sorry. So yeah, right. So that is what I've written over here, right? L of, so we have this equation L of psi of r comma x is equal to I of r x to the power r, and into this equation we put r equal to r1. So we get that, so this will imply that L of psi of r1 comma x is equal to 0. And remember that we wanted to find solutions of that LF equal to 0. So this implies that, and f is a function of x, right? So L of psi, since we have substituted r equal to r1, what remains is a function of x. So this is our first solution, and this is what we saw last time, right? So the first solution is y1x is equal to x to the power r1 times a n r1 x to the n. Okay, there's a question. Yeah, so the a n r's are analytic because they are ratios of polynomials and the denominator is non-zero. Yeah, I think, yeah, I explained that before I saw the question right now. Okay, so let's go to the next slide. So if R1 minus R2 is not equal to 0, then once again, we can just plug in R equal to R2. And so then we will get another solution, L of psi R2 comma x equal to 0, right? And the function, so this A and R2s, I mean, these are going to be real numbers, which makes sense because the A and R's are analytic at R2. So in, okay. Okay, so this is what we do last time. Did so much we did last time, but except that last time we just directly plugged in values R1 and R2 and we solved the, we did not bother to analyze the A and R's as functions. But looking at viewing the A and R's as functions has an advantage, and that is what we will see in today's class. Let us consider the case when I has repeated roots. So since I has repeated roots, R1 is equal to R2, it follows that for every n greater than equal to 1, the polynomial, the denominator does not vanish at R equal to R1. So it, yeah, that's obvious. So it is clear that the A and R are analytic in a small neighborhood around R equal to R1 equal to R2. Yeah, because the denominator does not vanish, right? So now let us apply the differential operator d by dr on both sides of the equation. Yeah, so we have this equation, right? Which is what we saw in, yeah. But using our functions a and r, we have this equation I of r x to the power r, and we just apply the differential operator d by dr on both sides. So what do we get? So we get this. So clearly the operators L and d by dr commute with each other. because yeah, because r and x are independent variables. So I'm just trying to say that suppose you take these two operators, d by dx and L is equal to x square d by dx, right? Let me call this operator f. Then your f compose L is not going to be equal to L compose f, right? In fact, I'm guessing that if you apply f compose L on the function x, it's not going to be equal to L compose f on the function x. But since L is a differential operator in terms of the d by dx's, and d by dr is, since r and x are independent variables, so this is fine. So anyway, so we can interchange the L and the d by drs. So that's what I've done over here. Now, psi rx is equal to, this psi rx is equal to a n r x to the power r summation n greater than equal to 0. And throughout this course, we have not been worried at all to exchange a differential operator and a sum. So we just take the, yes, let me remove this. Without any fear, we exchange the sum and the integral. So L into d by dr of summation n greater than equal to 0 a n r x to the power r n plus r, right? And we take this inside, we exchange both these. So then we will get exactly this, right? And this is equal to uh, d by dr of ir x power r, right? Because we, this is equal to this, and here we have simplified this. Okay, but what am I? Okay, but this thing on the other hand now, yeah, okay, great. That's the point. This thing over here, that's equal to this. Okay, so now we plug in r equal to r1 equal to r2 into the above, right? So the important equation we need to look at is this equality. We have to look at this equality, the fact that these two are equal, right? So we have L of a function of x and r is equal to this function over here. And now we plug in x equal to, I'm sorry, not x, r equal to r1. So now r equal to r1 is a repeated root of I of r, right? That was our assumption, that I of r has repeated roots, right? So this implies that I of r is 0 and I dash r is also 0, right? So when we plug in r equal to r1, so in this case, yeah, so then we will get that both these terms vanish. I dash r becomes 0 and I of r becomes 0, right? So therefore, we get this conclusion. So let me get rid of this. Therefore, we get that L of this function is 0, right? But now this function, it involves log x, so this should clearly not be equal to our earlier function. Well, okay, it's not so clear, but anyway, this is the second independent solution. No, this is going to be different, right? Because our first solution was exactly this. R1 is equal to R2, and our first solution was this thing. So summation, so let me just write on a new page. Right. So this is of the type L of summation n greater than equal to 0, a n dash R1. So here R1 is equal to R2, x to the power n plus x to the power n plus R1. So yeah, R1 is equal to R2. So let me not write L plus summation n greater than equal to 0. Okay, I'll write this as log x. An r1 x to the power n plus r1. Right? This is the function, let me say y of x. So is that L of y of x is equal to 0. Right? Now, notice that this is our first solution. Right? So obviously, I mean, yeah, this solution should not be equal to the first solution. Yeah. Yeah. Okay. It requires a proof, but it's kind of, maybe one can write a small proof, but it's almost immediate that it's, yeah, it cannot be equal that this function, it cannot, it will be like totally absurd if this is equal to summation n greater than equal to 0, an r1 x to the power n plus r1. Right? That would be totally crazy. But anyway, so let me go ahead. So let me see if there are any questions. Okay, there are no questions. So yeah. So here is the second solution. In the case r equal to r2. In the case r1 is equal to r2, when we have equal roots. So this is like really nice because uh, this time we treated the coefficients ans as functions. We defined those functions inductively, and then we did a nice trick which gave us a second solution. Okay. So maybe I can just go to the previous slide and pause over here for a few seconds. Yeah. Okay, so I hope this is clear. So this is second solution. I'm going to skip this example because both these, I mean, during the exam, I'm not, in the exams, I'm not going to ask any questions based on the case R1 is equal to R2, or this more complicated case where R1 minus R2 is an integer, positive integer. So I'll skip this. So you can take a look at this example if you want, out of for your curiosity. So let's skip this. But I decided to do this derivation because the derivation is interesting, and I mean, it has something new new in it, that we view these functions a and r as functions. We view these ans as functions now. We define them as functions now, and that, yeah, and that helps us. So finally, we are in the situation where r1 minus r2 is an integer, and it's a positive integer because we already considered the case 0 when it is 0. So we define capital N to be r1 minus r2. Okay. So once again, note that each a and r is a rational function in R. In fact, the denominator is exactly this. Fine, great. This is something which we have already seen. And let's look at this polynomial. So this polynomial an I equal to 1 to n I of I plus r evaluated at r2 vanishes if and only if n is greater than or equal to capital N, right? So let me explain this. Right. So let's look at this polynomial, right? So here we have this polynomial I of, so before that, let me make this, let me make a picture over here which will make things clear. Yeah. So this is my, let's say my R1 is here. I'm sorry, this is my R2 is here. This is R2 plus 1, R2 plus 2, R2 plus 3, and so on. And some R2 plus n, this is R2 plus n, right? So this is one root, R2, and the other root is R1. We are in this case, this is R1. Right? So when we look at this polynomial, so we are looking at I of 1 plus R2, I of 2 plus R2, I of 3 plus R2 and so on up to I of n plus R2, right? So if n is strictly less than, if n is strictly less than capital N, then this polynomial never vanishes, right? And the first time this polynomial vanishes is 1 plus R2 dot dot. The denominator does not vanish. And there's I of, let's say, n minus 1 plus R2. Then we have I of n plus R2. Okay, so I'm sorry, maybe I should have said. So I want these to be R, right? So I wanted to say that this polynomial, so this polynomial does not vanish at R equal to R2 when, yeah, if n is strictly less than n. So we are looking at this polynomial. Yeah, okay. And when n is greater than equal to n, when n is greater than equal to n, this polynomial vanishes at R equal to R2. So we are looking, yeah. So then, so we will have I of, yeah, right. So we will have somewhere over here, we will have a I of n plus R, right? So when we plug in R2, this will vanish to order exactly 1 because this is a quadratic. There's going to be a quadratic equation which has, yeah, which has root R2, yeah, R1 plus n and R2 plus n. Yeah. So anyway, so this will vanish exactly to order 1 at R2, and the remaining ones won't vanish. Okay. Okay, so I hope my point is clear, and if not, you just think about it. It's a simple point. Uh, so let me go back to the previous slide. So this is the line I was trying to explain all this while. This line. Yeah. So thus, if we define a n r is equal to as the small a n r into r minus r2, then it is clear that for every n greater than or equal to 0, the function a n r is analytic in a neighborhood of r2. Okay. So yeah. So we have our a n r's. So let me go back to this page and explain. Oh, sorry. Yeah. So we have our functions a n. We have our functions a and r's. This is some polynomial in R divided by this I of 1 plus R, I of 2 plus R, and so on up to I of n plus R. Right? Now here the denominator vanishes. Denominator vanishes at R equal to R2 to order at most 1. Right? So therefore, if I just multiply a n r with r minus r2 over here, then that will get cancelled away. There's some polynomial p of r into r minus r2. Okay, that r minus r2 will get cancelled away. Or okay, let me not write. It may not get cancelled if the n is smaller than n. So this is an r minus r2, right? Divided by this thing, I of 1 plus r dot 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 I of n plus r. So if my I of capital N plus r is coming over here, then this r minus r2 will get cancelled, will cancel off a part over here, right? So the point is that therefore, so this implies that, and then the remaining, it'll get cancelled off, and then the remaining thing, for the remaining thing, the denominator does not vanish. So the point is that this is what I've defined, a and r. This function is analytic at r equal to r2 for all n greater than equal to 1. All these functions are analytic. Okay, that's the point we made in this slide. So let me go back to presentation mode. Yeah, let me just give you guys a few seconds to think about this. Okay, there are two questions. So how did we write L psi Rx is equal to I? That is something which I explained earlier, right? So let me just, so L of psi Rx is equal to summation n greater than equal to 0 En x to the power n plus r. And the Ens, we saw the expression for the Ens, and the functions a and r were defined by the condition En is equal to 0. Right? So only E0 remains. So I hope that is clear. So let me just go back once. Where is that slide? Right? Let's look at this equation. So to begin with, we did not make any choices for A and R. So let me just make this a little bit bigger. So to begin with, we did not make any choices for A and R. But after that, we got this equation, L psi, and this is the E and R. After this, we define, so we find, okay, if you like, I can call this a new psi, let's say define phi Rx. So I can say that, if you like, I can say define phi Rx by, so yeah. So I don't know, I can, if you want, I can say phi Rx is equal to summation n greater than equal to 0, a n r x to the n plus r, where these a and r's are defined by this equation over here. Right? So now when I compute L of phi Rx now, what is this going to be? This is going to be summation n greater than equal to 0, En x to the n plus r. But now by our definition of A and R, all these Ens are going to be 0 for n greater than equal to 1. So we are only going to remain with E0 x to the power n plus r. Okay. And E0 is I of R, AR, A naught R, and A naught R we took to be 1. Okay, so let me go ahead. So I hope this is clear. Otherwise, you can ask me at the end of the class. So where was I? Okay. So we were here. Sorry. So the point I was trying to make is this function is is A and R is analytic in a neighborhood of R2 for every n. Okay, so let's go ahead. In particular, A n R2 and A n prime R2 are well-defined real numbers. So that's great. So now we are going to apply the same trick. Okay. So uh, we multiply the equation L psi Rx equal to IR x to the power R with R minus R2. So we get this thing, R minus R2 into L psi Rx is equal to, so once again, R minus R2 and L, we can interchange those two because L, okay. And this is equal to, all right, yeah. So maybe yeah. So this on, sorry. This object is equal to, on the one hand, it's equal to L R minus R2 into psi of Rx, this whole thing. And on the other hand, this is, since these two are equal, the product of these two is up. So the operative thing we need is this thing, this equality. Okay, so let's go ahead. So, and notice that this thing is equal to this thing because psi was equal to summation n greater than equal to 0 a n r x to the power n plus r. And by definition, this capital A and R is obtained by multiplying r minus r2 with a and r. Okay, oops, fine, right? So now we will, so let's see. So now we will apply the differential operator d by dr on both sides of the equation, of this equation, right? So in the previous slide, we got this equation. And now we do the same thing. So we will apply the differential operator d by dr. So here we exchange L and d by dr. That's something which we can do. And yeah, so this thing is just d by dr acting on this side. Okay. And that is equal to this thing, right? Okay, great. Yeah. So now what do we have? We have that at R2, this guy vanishes because this is I of R. Here we have R minus R2. So this thing vanishes. And here also we have R minus R2. So this thing also vanishes, right? So cool. So thus we get uh, L of, so, right. Okay, I don't know why I have written this twice. I mean, both these are equal. Yeah, sorry about that. Uh, so, yeah, I need not have written this. Yeah, this thing I can cancel off. This thing is equal to L of, yeah, I just differentiate this and I get this. Okay, yeah, so fine. So, yeah. So this is the equation that we need. This is the equality that we need, right? That these two are equal. And now we are just going to, as before, we are going to put R equal to R2, which is what I'm doing in the next slide. So we get the right hand side as 0. Okay, so we get the second solution. Okay, so I hope the method is clear, and it's the method that is, well, it's not so important. It's interesting. It's not important from an exam point of view, but it is very interesting. So that's the reason I chose to do this. But I don't want to, I'm going to skip this example because in the exam, I'm not going to give any questions related to this case or the case R1 is equal to R2. But in the exam, there are questions which are related to the case R1 minus R2 is not an integer. In fact, that is there in this quiz. So I suggest you practice some questions. Okay, so let's quickly zip through this example. You can, if you find it interesting, you can look at it in your free time. So let's just summarize the situation. While solving an ODE around a regular singular point by the Frobenius method, the cases encountered are roots not differing by an integer, repeated roots, roots differing by a positive integer. So the larger root always yields a fractional power series solution. So by this complicated term, we simply mean something like this, right? A n x to the power n plus r. And r can be a fraction. So yeah, I mean, r can be any real number, I suppose. So therefore, yeah. So in that sense, this word fractional is not so great because yeah, we can have roots which are anyway. So in the first case, the smaller root also yields a fractional power series solution. So this in the first case, that is this case. In this case, the smaller root also. In the second and third cases, the solution may involve a log term. Okay, so that sort of brings us to an end of this discussion. So uh, I will stop sharing this slide and go on to uh, the next chapter. So let me stop sharing. And now I want to share this one. Okay. So I hope my screen is visible. Uh, Once again, can someone please message me on chat if my screen is visible? Yeah, thank you very much. Yeah. Okay, so let us write down some classical ODEs. So this is the Euler equation. This is the Bessel equation. We will next look at this case more closely, and Laguerre equation. Okay. Okay. I don't know why I wrote this classical equations down, but I mean the point is we are going to look at this equation, right? So this is in the regular singular case, right? Because this is, yeah. So we have y double prime plus uh, y prime 1 upon x plus x square minus nu square by x square, y equal to 0. And when I multiply this with x into 1 by x, this is analytic, and x square into x square minus nu square by x square, this is analytic, right? Therefore, this is the regular singular case. This is an example of what we have just seen so far, and we are going to do that. But before that, I want to talk about a little about the gamma function, because we will use the gamma function. Uh, so strictly speaking, we don't need the gamma function in our course, but it's a very interesting function in mathematics. It's a function which comes everywhere. So I thought it would be interesting to speak a little bit about it. So it's defined, we want to define the gamma function on, let's say we want to define it on the complex plane. So, well, for those of you who have done complex analysis, it will be a little bit insightful for you, but perhaps others will not find it this discussion so insightful. So we want to define the gamma function on the complex plane. So we define it by an integral. Okay. So this is the point 1. And in this region, we define this gamma function like this. So P belongs to complex numbers such that real part of P is greater than equal to 1, let's say. Well, okay, maybe just to be safe, I just say strictly greater than 1. Okay. So this function is defined in this region to begin with. And there is a problem if p is strictly less than 1, since t to the power p minus 1 is unbounded near 0. So if you look at this, if p is strictly less than 1, so then this becomes something like, let's say p is half. If p is half, then this is e to the power minus t divided by t to the power half. And as t tends to 0, this function, it tends to infinity as t tends to 0, right? So this integral is not going to be finite. I mean, yeah. So this function is not a nice function. Right. Well, okay. So anyway, it's not, or at least it's not clear immediately that this integral is nice or not. Okay. So for p strictly greater than 1, there is no problem because e to the power minus t is rapidly decreasing. Yeah. So for p strictly greater than 0, the graph of this function over here, it looks like something like this. For p strictly greater than 1, I'm sorry. It looks like this, right? Probably. Right. So when we integrate from 0 to 1, we are going to get this finite quantity, this number. So gamma of 1 is 1. And this is the most important problem. So this is the only point that I really want to emphasize. So for any real number p greater than or equal to 1, we get gamma of p plus 1 is, so we write it like this in this limit, right? So I mean, I'm just taking the limit because I don't want an infinity over here. So this is, and here we use uh, integration by parts, and this thing is equal to p times gamma p. Yeah. So the real point I want to make is gamma p is equal to p times gamma p plus 1 is equal to p times gamma p, right? So although to begin with we defined the gamma function only in this region, we are now going to use this function which is defined as in this region. It satisfies this amazing property, okay? And we are going to use this property to extend the definition to the left. Yeah, to the left. We will extend the definition to this region. So let's see how we do that. So gamma of p plus 1 is equal to p times gamma of p. That means gamma of p is equal to gamma of p plus 1 by gamma of p. So we do exactly that. So what do we do? So we have this region. So let's say p is a point over here. So now we just define gamma of p, the value of gamma at this point is equal to, I go to p plus 1 and then I just divide it by p. So here this is going to give me gamma of p plus 1 and then I divide this by p. So this is p, there is some complex number p, right? So this now allows me to extend my gamma function to this region. Right? For any p over here, my value, my gamma function is defined. Okay. Now I can, so if I want to define gamma of 0, then I will have gamma of 0 is equal to gamma of 1 divided by 0. So there is going to be over here the gamma function will blow up. Let's say we don't want to define it over here. Let's look at this region now. Let's look at this region, right? So once again, we can do the same thing. We can, the value of the gamma function here at this point can be defined at the value here divided by this p. So we use star to extend the gamma function to all real numbers except non-positive integers 0, -1, -2, dot dot. So we cannot define it at these negative integers because it's not, we will not be able to define it at 0. And since we have not been able to define it at 0, we will not be able to define it at -1 and -2 and so on. But at all other points, we can define the value inductively. Like we can just keep, yeah. So if I want to define the value at this point, then first define at this point. To define at this point, we define at this point. And over here, it is defined by the integral. Defined by the integral. Okay. So if p strictly lies between 0 and 1, then p plus 1 lies between 1 and 2, and hence gamma p plus 1 is defined. So we use star to define gamma p. This is what I explained right now. Next, suppose p lies between -1 and 0. This implies p plus 1 lies between 0 and 1. Since gamma p plus 1 is defined above, so in using this step, gamma p plus 1 is defined now. Okay, proceed like this. So this, yeah, okay. So for example, gamma of -5 by 2 is, should be defined like this. So we repeatedly use this equation. Okay, let me go ahead. So and this is, so let me just choose the next picture. So at p equal to 0, if we approach from the right, then the gamma function tends to infinity, and if we approach from the left, then the gamma function tends to -infinity. Yeah, I think I'm just going to go through these slides very quickly. It's easier to explain this on the board, but anyway. So though the gamma function is now defined for all real numbers except the non-positive integers, the integral representation is valid only for p strictly greater than 0. So what I'm trying to say here is, so we have the complex plane. And if you understood what I'm saying, we would have defined the gamma function as a nice function at all points. So let me make these as open circles. At all points except these. Okay. However, to begin with, we defined the gamma function in this region by an integral. So this is gamma of p is equal to integral 0 to infinity, I think t to the power p minus 1 e to the power minus t dt, right? But if you take a point over here, or wait, let's not take a complex point. If you take a point over here, and if you try to evaluate this integral, then you will get the answer, your answer will be infinity. So I'm just trying to say that this function over here gives the value of the gamma function only when p is strictly greater than 0. Okay. So it is useful to rewrite. So we had this equation, gamma of p uh, is equal to gamma of p plus 1 by p. Okay. And we will rewrite this equation like this. Okay. And now the function, so the function gamma of p was not defined at 0, minus 1, minus 2, and so on. Yeah. But the function 1 upon gamma of p, well, okay, have I not meant? Just 1 second, I'm sorry. Okay, there is an important point which I have not mentioned over here, a very important point. So let me just say that the gamma function, let me write that down, sorry. So far we defined the gamma function on the complex plane minus the negative integers, I mean non-positive integers, right? So important theorem, right? So the gamma function does not vanish, is never 0. And so on. Okay. And therefore, the function 1 upon gamma of p is a nice function on C minus. Okay. So define, or rather one can check that limit p tending to minus n 1 upon gamma of p is equal to 0. Okay. So what I'm trying to say is the function 1 upon gamma p is defined everywhere except these points, right? Because gamma p never vanishes outside. So, and at these points, when you look at the limit, these limits are 0. Yeah. So gamma of 1 upon gamma p is becoming smaller and smaller in neighborhoods. So therefore, we can just define 1 upon gamma p to be. So if we define 1 upon gamma p to be 0 at p equal to 0, minus 1, minus 2, and so on, then we get a very nice function. Okay, so all this is very theoretical, and yeah, I'm sorry. So yeah, but we will use one property of the gamma function. We will use something that we will use one this property, that 1 upon gamma p is 0 at these, at 0, minus 1, minus 2 later on. So when that point comes, I will explicitly mention it. But let's just quickly go ahead. Enough of the gamma function. So let's look at the Bessel equation now. So the gamma function will come in our discussion of the Bessel function. Yeah, so it should be p strictly greater than, yeah. So questions related to gamma function we could take after today's lecture. So the Bessel equation is a second order linear ODE. This x square y double prime plus xy prime plus x square minus p square y is equal to 0. So its solutions are called Bessel functions. Bessel functions have application dot dot. Since x equal to 0 is a regular singular point of this thing, we get a Frobenius solution. This is called Bessel function of this first kind. So we are following the standard template now that we saw earlier. So okay, fine. So the Frobenius, for how do we get the Frobenius solution? We put y of x equal to this x to the power r, a n r, x to the n. Basically we first find the initial equation. We don't do, yeah. We find this initial equation. So remember what it was, r into r minus 1 plus b0 into r. Here b0 is just the constant function 1, right? So remember x square y double prime plus x bx y prime plus c of x into y equals 0, right? So yeah, so b of x here is clearly 1. What is c of x? C of x is equal to x square minus p square, right? So b0 is 1 and c0 is minus p square, right? So plus b0 into r plus c0, right? So this is r square minus p square. Great. So the roots are r1 is p and r2 is minus p. So, and how do we get the recurrence relation? We equate the coefficient of x to the n plus r to 0. So then we get, so this is one equation that we get. And the second, yeah. So these are the two equations that we get, right? This is the one that we get for n equal to 1, and for n greater than equal to 2, we get this. These are the recurrence relations we get. Okay. So now notice that uh, this this forces that this function a1 is 0, right? Because r plus 1 whole square minus p square, this we are viewing it as a function of r now. So this means that the function, so this is a non-zero function. P is fixed, but r is not fixed. R is, we are treating it as a variable. This is a non-zero function. This into a1r is 0. That means a1r is the 0 function, right? And now the previous relation tells us that an minus 2r and anr, they satisfy this equation. But that would mean that all the odd terms are 0. So that's how we get this. And the even terms, I hope this is clear, right? Because first we get a1r is equal to 0. This equation we get as part of the recurrence relation. And this equation will imply that a1r is a function of r is 0. And then we plug that in into this equation. So we get all the odd ans are 0 as functions of r. And the even ones are this, have this form. And we have taken a0r to be 1, the constant function 1. So let's just stare at this for a few seconds. Okay, so let's go ahead. For the Frobenius solution, set r equal to p, the larger root. And this is, yeah, so that's exactly. We have these functions a and r. So here the odd ones are 0. So we look at a, 2, and r's. And we put the two solutions are p plus minus p. So the larger solution is p, and we set that. So we get this thing. So we get these coefficients, and this is the solution y1x, and we know that y of x, it converges in 0 comma rho, where rho is equal to minimum of radius of convergence of b of x and c of x around 0. Okay, so this is, we get the first solution, and we multiply y1 of x by this factor, 2 to the power p into by this factor, and then that will get us into this convenient form. Okay, so here we will use this. So when we multiply this thing with this guy, and after that when we use that property of the gamma function, gamma of p is equal to gamma of p plus 1 by p, then you can get this into this simpler form. Okay, okay, great. This is called the Bessel function of first kind of order p. Okay, so I've just written it once again. So let's just see two Bessel functions. This Bessel function of order 0 and this Bessel function of order 1. So here the p is 0 and here the p is 1. Okay, fine, nothing great. So here are some, I don't know, some properties of the Bessel function, which just for interest, you can just look at this diagram and, you make some graph. So both J0 and J1x have damped oscillatory behavior. So they oscillate. So you can see that they are oscillating. And I suppose that this height is, I don't remember what it's called. Can someone remind me? Is this called the amplitude? Yeah, I don't remember right now. Maybe you guys know this better. Uh, okay, so let me go ahead. And they satisfy derivative identities similar to cos x and sin x. Okay, so recall that, so we are not going to do this analysis at all. So recall that r1 is equal to p and r2 equal to p are roots of the initial equation. So that r1 minus r2 is equal to 2p, right? And p here is a real number. So the analysis to get a second independent solution of the Bessel equation splits into the following cases. 2p is not an integer, 2p is an odd positive integer, 2p is an even positive integer, and p equal to 0. Okay, so I have written the analysis. It's very complicated and kind of boring. So, and there are going to be no questions in the exam related to this. So I'm just going to skip through it. So if those of you are interested, they can look at it. But this part is important. And in the exam, I'm definitely going to ask, not in this quiz, but in the end sem. So in this quiz, I'm definitely, in the end sem, sorry, not in this quiz. In the end sem, definitely there are going to be questions on the Bessel function, but those questions will only use some simple properties of the Bessel function. So let's summarize. For every real p, we define this series. And so notice that whenever we define a series, we want to make sure that the coefficients are real numbers. So there should not be infinity. So this coefficient can be infinity only if this gamma function, it vanishes. But from I had stated this theorem that the gamma function never vanishes. So the above is a well-defined power series once we know that the gamma function never vanishes. Okay. So if p does not belong to 0, 1, 2, dot, 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 then jpx and j minus px are the two independent solutions of the Bessel equation. Okay. And if p belongs to 0, 1, 2, dot, 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 then j minus px is equal to minus 1 to the power p j of px. So this is left to you as an exercise. I would strongly recommend that you do this exercise. And to do this exercise, you have to use the vanishing of 1 upon gamma p for p belonging to 0 minus 1 dot dot dot. Okay. So I would very strongly recommend to all of you to do this exercise. It's in your tutorial sheets. And yeah. So the only purpose of this, yeah, exercise is to sort of, yeah, I suppose, yeah, is to use this property of the gamma function. So let's go ahead. So the Bessel functions, they satisfy some Bessel identities. So let's see what these are. So these are the Bessel identities. So there are two Bessel identities. Okay, so you can look at them. And the above two can be obtained by formally differentiating the power series. So you just write down the power series for jpx, multiply it with x to the power p, and apply the derivative. And you will see that you get this. Okay. And then you have these two identities. So these two can be derived. These follow from 1 and 2. So expand the LHS of 1 and 2 and divide by x to the power plus minus b. So 3 and 4 can be obtained from 1 and 2. And then we have 5 and 6. I suppose 5 and 6 can be obtained from 3 and 4. Okay. Add and subtract 3 and 4 to get 5 and 6. Okay. Okay. So maybe I will stop for today. I wanted to go up to this very interesting theorem of Liouville, but so I wanted to go up till here, which is a very interesting theorem. But maybe we will start with that next time. Okay. So we will stop here. I will now take questions if there are any. So if you did not understand the discussion on gamma function, or if you had any difficulty with it, do not worry about it. The only I would only suggest that you do this equation, this problem. Okay, this problem is there in your tutorial sheet also. You just have to do this problem, and the only property of the gamma function that you have to remember is this. Well, one property you have to remember about the gamma function is this, and the other property is that gamma p is equal to gamma p plus 1 by p. Right. Yeah. In slide 6, yes. So I mean, actually, you're right. Someone has asked, sir, in slide 6, shouldn't the integral form of the gamma function be valid for p strictly greater than 1 instead of p strictly greater than 0? Let's see. What have I written on slide 6? Well, I think the integral representation will be valid for p strictly greater than 0 also. So, I mean, if you integrate this 0 to infinity t to the p minus 1. So let's just take p equal to half. I think this integral will still be finite, although I'm not sure. Integral 0 to infinity. Let's just take half, okay? T to the power half dt. So although this function, it does blow up at 0, but I'm guessing that the integral will still be finite. Is that correct? I'm not sure. Well, to be safe, you can, okay, if you want, I can just write. I mean, the point is that we define the gamma function by an integral for, to be absolutely safe, let me just take p greater than 2. We define the gamma function using an integral on a suitable right half region, right? And then we can extend it step by step to these regions. That's the only point I wanted to make, right? Yeah. So we define it in this region first, and then step by step we extend the function into these regions. So that's the only point I want to make. Yeah. Now if you really like to integrate things, if you really like to compute things, then you can try to investigate if this integral is finite or not. Yeah. So I think from my memory, uh, in Frobenius, okay, in Frobenius series, did we discuss how slash why the solution series converges? No, we did not discuss that at all. We just stated that as a theorem. We we discussed how to get the series, and the theorem was that. So okay, let me add a page over here. Okay, let me go to the last page. I was yeah. So I will add a page here, and now I will write down all my discussions. So why does it converge? Well, there are many whys in this course which we have not touched at all. So I suppose this is one of those whys. Yeah. So we only discussed how to get these ans, x to the power n plus r, right? How to get one solution, let's say the larger one. And then we just stated it as a theorem that this solution, it makes this power series, it makes sense in the open interval 0 1. It's a nice function in the open interval 0 1. I'm sorry, not 0 1, 0 rho. And what is rho? Rho is equal to minimum of radius of convergence of b of x and c of x around 0. Okay, this is, we stated this as a theorem. So I hope that answers the question. Yeah, as far as this question is concerned, so why does it converge? Well, I don't know. It's probably some deep theorem in differential equations. I am no expert in differential equations. Well, one of the reasons, also we said it converges in minus rho comma rho. Uh, no, okay, I don't know. I will look at the slides again, but the important thing is, maybe that's not necessary. The important thing is that it converges in 0 comma rho. Well, one reason to not look at minus rho comma rho is because, this is something like x to the power half times some nice series, right? A and x to the power n. Surely you expect this function to behave badly at 0, right? Right? This x to the power half, you expect it to behave badly at 0. Therefore, this entire function, it will not behave well at 0. Right? So we should only expect convergence in 0 comma rho. So I will look at my slide once again. I don't know what you're referring to, but I don't think I said that it converges in minus rho comma rho. If I said that, if I wrote that, that is not correct. Yeah. I hope that answers the question. Like even like philosophically, a lot, not philosophically. I mean, from our intuition, from, I don't know. Yeah, this x to the power half is obviously going to not behave well at 0, right? So obviously we should not expect this function to extend across 0 in a nice way. Okay. Any other questions? So as far as the exam is concerned, I don't think you people have to worry too much about any theoretical aspects. I mean, or rather, you should. Yeah, I think all the exams and the quiz which are going to, all the questions which are in the quiz, um, are of the nature where you should have understood the process and you have to execute the process correctly. So I would suggest that you guys uh, remember what the recurrence relation is in the Frobenius method, And because otherwise, if you sit down to derive it in a 1 hour quiz, you will be in serious trouble. So there is only one question which is somewhat tricky, I would say. All the other questions are so there are some very basic. Yeah. Anyway, I will write an email describing something about the quiz which is going to happen. Okay, so if there are no other questions, then let us end this meeting. Okay, thank you everyone for coming. Okay, so there's one question. Why is the denominator of an product, shouldn't it just be I and R? Okay, so this is a good question, so let me try to address this. Okay, but before that, right. Okay, so what did the equation look like? No, I suggest, so I suggest that you write down two terms and then it will become clear. So the equation looked like I n plus R a n plus something. Okay. So let me say some. mm, okay, let's say this is some p0r. Okay, is equal to 0. I'm sorry, not p0r. This. Okay, this is going to be I equal to 0 to n minus 1, b n minus I plus r, ai plus c n minus ai equal to 0, right? Now, to answer a quick answer to your question is that already the ai is contained the. Yeah, okay. So let's just look at some examples, right? So that will become make it clear. So this will be one. When I put n equal to 1, I get a1 of r plus what is this going to be? This is going to be some polynomial, right? So let me just write it as p0r equal to 0. Okay. So this will imply that a1 of r is equal to minus p0 of r divided by I of 1 plus r. Right. Now the equation for 2 is going to look like a2 plus r, a2 of r plus uh, something into a0 of r, that's 1, plus something into a1 of r, that is going to be a1 of r is p0 of whatever minus p0 of r divided by I of 1 plus r, right? Yeah, plus something into whatever. Okay, so I hope you get the point. So I can write this as something times a0r plus something times a1r is equal to 0, right? So this will imply that a2 of r is equal to, now a1r is, so I'll absorb that something into this star divided by 1 plus r, right? And then I can clear denominators, and so this is going to be minus something divided by I of 1 plus r into I of 2 plus r, right? Now when we go to I of 3 plus r times a3 of r is equal to, yeah, once again something times a0r plus something times a1r plus something times a2r, right? So you see the pattern. I hope this is clear now. Yeah, okay. So because here, so this is going to be something times, so here there's going to be nothing, some polynomial plus something divided by I of 1 plus r plus something divided by I of 1 plus r into I of 2 plus r, right? Now once again we clear denominators and we write this whole thing as I some whole something on top divided by I of 1 plus r. So when we take this down, yeah. So I hope that is clear. Any other questions? Okay, thank you very much. If not, we will end today's session.